Imagine for just a second taking a one-way journey into absolutely the most extreme, hostile environment in the entire universe. Welcome to our latest explainer. Today, we're taking a cinematic voyage right into the dark heart of a black hole. Now, we're going to strip away all the sci-fi tropes and look strictly at what our most advanced physics, from gravitational wave detectors down to the raw math of general relativity, actually tells us about the fate of matter when it falls into the abyss. It's a journey where the very fabric of space and time bends, breaks, and honestly completely defies our current understanding of reality. So what would actually happen if you crossed the point in space from which absolutely nothing, not even light, can escape? This is the central mystery driving this whole explainer. What happens when matter is pulled past that ultimate point of no return? For decades, this question has completely haunted astrophysicists. We know matter falls in, right? But it doesn't just quietly vanish. To understand the terrifying yet incredibly fascinating physics at play, we need to trace the path of a doomed object step by step as it approaches, crosses, and descends deep into the gravitational well of a black hole. Okay, let's dive right into section 1. What is a black hole? Before we go falling into one, we've got to understand exactly what it is we're approaching. This definition here, it comes straight from the gravitational wave observations cataloged by the LIGO and Virgo collaborations. You see, a black hole isn't just an empty hole in space. It's a region of space-time packed with so much mass in such a microscopic area that its gravitational pull becomes absolute. Because literally nothing, not even light, is fast enough to escape its grasp, a black hole is essentially invisible against the dark canvas of space. Now, what's wild is that our journey will actually scale depending on the sheer mass of the black hole we approach, because they come in a few distinct sizes. First, we have stellar mass black holes, which are born from the catastrophic supernova collapse of massive stars. Then, way at the other end, we've got the true heavyweights, the supermassive black holes anchoring the centers of nearly every single galaxy, including our own Milky Way. And right in between, we have intermediate mass black holes. These are kind of rare, missing links. Actually, astronomers using the Hubble Space Telescope recently found some incredibly compelling evidence of one of these elusive intermediate black holes hiding right in the Omega Centauri star cluster, just yanking on fast-moving stars right at its core. But because we can't see them directly, we've had to build a massive catalog of indirect, observable evidence to prove they're really out there. We use the Event Horizon Telescope to capture the glowing shadows of supermassive black holes, like M87 star. We use gravitational waves to literally listen to the ripples in space-time when two black holes collide. We watch the orbits of stars being whipped around by invisible forces. But here's the catch. Everything we can observe happens outside the black hole. So, what happens when matter gets too close? That brings us to section 2, the accretion disk. Well, before reaching the black hole itself, matter faces some extreme consequences in what is essentially the chaotic waiting room of the abyss. This quote vividly describes a tidal disruption event, specifically one observed by NASA's Swift Observatory, where a wandering supermassive black hole literally shredded a star. When matter, whether that's gas, dust, or just a really unlucky star, approaches, it doesn't just fall straight in. No, it gets caught in this insane gravitational whirlpool. It spirals inward, forming an incredibly dense, rapidly spinning accretion disk. The friction inside this disk is so intense that the matter is superheated to millions of degrees, blasting out powerful X-rays and radiation. It's basically matter's incredibly violent last stand before crossing the threshold. Moving on to section 3, the event horizon. We have now arrived at the critical threshold. But you gotta remember, this is not a physical, solid surface you could just go up and knock on. It's a boundary in space-time where our very perception of reality splits. Because of a mind-bending phenomenon in general relativity called gravitational time dilation, time actually behaves completely differently depending on where you are. To a faraway observer watching you fall toward the event horizon, the extreme gravity warps time so severely that you'd appear to slow down dramatically, basically freezing as you slowly fade from view. But for you, the person actually falling, your watch ticks completely normally. You would cross the event horizon totally smoothly. You wouldn't hit a wall. You would just seamlessly slip right out of the observable universe. All right, section 4, extreme tidal forces. So here's the thing. Once we cross that horizon, we leave direct observation behind entirely. No telescope in existence can see past this veil. From here on out, we are relying completely on the predictions of theoretical physics. And let me tell you, general relativity predicts a genuinely terrifying physical progression. First comes a process that physicists brilliantly named spaghettification. Because gravity gets stronger the closer you are to the source, the downward pull on your feet would be vastly stronger than the pull on your head. You'd literally be stretched out radially like a piece of spaghetti and squashed in from the sides. But the physics actually gets even stranger. Deeper inside, especially in charged or spinning black holes, theoretical models suggest these forces actually change signs. You would transition from being stretched into a noodle to being violently compressed in all directions at once, a process physicists half-jokingly refer to as pancakeification.
Let's plunge right into Section 5, Inside the Horizon.
Let's delve even deeper into this theoretical interior. This is a region that is fundamentally different from ordinary space, where the geometry of spacetime itself drives matter relentlessly inward. Since we obviously can't send a probe in and get data back, our entire understanding of this deep interior relies on incredibly complex mathematical models, specifically the geometry of Reisner-Nordström spacetime. Now, this isn't just arbitrary math on a chalkboard. This is the geometric scaffolding of reality itself inside the black hole. It predicts the existence of secondary, inner horizons, where the flow of space begins to act in highly counterintuitive ways. And it's these exact mathematical models that predict the violent physical shifts we just talked about. We use complex differential equations to dictate exactly when and where those radial and angular tidal forces flip. It's this math that tells us an infalling observer doesn't just fall smoothly forever, but is instead subjected to a brutal washing machine of stretching and crushing gravitational tides. As matter plunges even deeper, approaching what physicists call the inner horizon, things get apocalyptic. The equations predict a classical blue shift instability. Remember Hawking radiation, those quantum particles emitted at the event horizon? Well, near the inner horizon, an infalling observer would be met with an incredibly roiling, dense atmosphere of this quantum radiation. In fact, semi-classical calculations suggest this creates a literal wall of practically infinite energy. It is a profoundly hostile environment, where all the intense forces of the black hole are completely concentrated. Which leads us to Section 6, the ultimate scientific mystery. Finally, whatever is left of our falling matter reaches its ultimate destination. This is where the known laws of the universe simply collapse, this singularity. Now, I want to make this absolutely clear. Scientists do not know what physically exists here. In classical general relativity, all the mass of the black hole is said to be crushed into a space-like region, a point of infinite density. But physicists know that infinities usually mean your math is just broken. The singularity really represents a hard limitation of our current theories. It's a massive, glowing neon sign that says general relativity is incomplete, and that to truly understand the heart of a black hole, we desperately need a complete, unified theory of quantum gravity. And that brings us to the ultimate puzzle. When matter, along with all its unique, fundamental quantum information, is crushed into the singularity, and the black hole eventually evaporates over eons via Hawking radiation, what happens to that information? Is it perfectly preserved in the outgoing radiation, or is it permanently, irreversibly destroyed? This is Hawking's information loss paradox. It remains one of the single greatest unresolved problems in modern physics, sitting squarely at the messy intersection of gravity and quantum mechanics. So, we've tracked matter from the intensely chaotic accretion disk, past the time-bending event horizon, through the crushing, bizarre forces of pancakeification, right down to the very boundary of human knowledge. But the final fate of matter remains totally locked away. It forces us to ask, if our current laws of physics cannot fully describe what happens at the heart of a black hole, what new law of nature are we missing? What secrets are waiting in the dark? Keep questioning, keep looking up, and we'll catch you in the next explainer.